Hi and welcome to this presentation about how to stop complex fraud in its tracks with Neo4j and graph databases. My name is Alessandro Svensson and I will present this topic together with Nab Matter, who is our Senior Director for Global Solutions at Neo4j, and Ryan Boyd from our Developer Relations team. We will start off by talking about some of the challenges that exist in the world of fraud detection today. We will discuss fraud rings in particular, and how existing fraud detection systems can be augmented with graph database technology to help prevent such fraud schemes. After that, we will take a deeper dive into a few examples of credit card fraud and also do a demo of Neo4j. We will also go over how Neo4j would fit in a typical fraud detection architecture. Okay, so let's start by taking a look at who today's fraudsters are. Well, unfortunately, fraudsters today are often more sophisticated than most systems one would have in place to prevent them. The biggest fraudsters usually don't operate as lone anomalies today. Rather, instead of an individual, fraudsters are typically organized in groups. Instead of using their own identity, they manufacture identities, and also called synthetic identities. They also perpetrate fraud using stolen identities and hijacked devices. Of course, there are many different types of fraud, and all with their own sets of complexity. A very prevalent fraud type is credit card fraud, which we will address a little later in this presentation. Merchants themselves can be fraudulent. Fraud rings are a huge problem and very hard to detect and stop with traditional systems. Insurance fraud is of course very widespread, as well as e-commerce fraud. But perhaps the most important fraud is the fraud that we really don't know about yet. The challenge with fraud, especially from a data perspective, is that it can be so many things at the same time. First, it's constantly evolving. It can appear both simple and complex at the same time. Sometimes a scheme involves few or many players. It appears in both digitized and analog forms. And there's always that sensation that fraud is kind of one step ahead. So let's talk briefly about fraud from a data modeling perspective. Because of the complex and varied nature of fraud, all the detection efforts we have in place stores enormous amount of raw data. For example, you can think about it in terms of storing every transaction being made over a period of time for a large bank. That is a huge amount of data being stored on a daily basis. And finding clear anomalies is one sort of traditional way to go about detecting fraud. A credit card couldn't be in two different locations at the same time, for example. The real challenge emerges when the anomalies themselves hides in normal behavior and only become apparent through the exposing of patterns. These patterns can occur in many different ways and complexity. However, the job for the fraud prevention team is basically to react to these patterns by first detecting them and then respond to them. And of course, doing all this as fast as possible. The key to achieve this is very much a question of choosing the underlying technology. If you store your data like this, as you would in a relational database store, you will probably have a pretty good success with your discrete analysis, finding the anomalies we talked about earlier. However, if you're looking to detect and respond to patterns, this structure won't be anywhere near sufficient. Instead, what you need to do is reimagine your data in the way that it's connected, which is of course data modeled as a graph. And this is how data is stored and queried in a graph database like Neo4j. Okay, let's have a look at one example. Let's have a look at how fraud rings can be prevented using graph database and connected analysis. First of all, I'd like to start off with the statement from Gartner, which basically says that it's obvious that traditional technologies which were aimed at individuals and their behavior are inadequate to detect and prevent sophisticated fraud, and especially fraud rings. So why is that? Well, let's have a look at what traditional fraud detection looks like. Traditional systems are often what we call either endpoint-centric, navigation-centric, or account-centric. An endpoint-centric solution analyzes the characteristics of a computer or a mobile device, for example, that is used to access different systems. An example of navigation network-centric solutions analyzes the navigation of a session, usually by IP address and user ID, to see if it looks anomalous relative to normal user or peer group behavior. Account-centric solutions is all about in which transactions are compared to what is expected of the user or the entity. To support identity prong, this layer could also include integration of external and internal data to help vet an identity, especially in a risky transaction, such as a new account application, for example, or to verify a suspect authentication or a high-risk transaction. What all these methods are examples of is discrete analysis, which is very effective if you know what to look for. The weaknesses, though, are that discrete analysis do a poor job when you want to detect fraud rings, for example. When someone is using a fake IP address, when you're dealing with hijacked devices or synthetic identities or stolen identities, etc. The challenge with systems that focus on discrete analysis for fraud detection is their inability to detect fraud rings or synthetic identities, as this requires additional context. So let's take a look at a simple example. In this simple fraud detection approach to detect a credit card fraud, it's relatively easy to spot outliers. That is, the data points that you know that you need to investigate. But what if the fraudster that commits the fraud while still exhibiting normal behavior? Well, that is exactly how fraud rings operate. A fraud ring rarely strays outside the normal behavior. Instead, they operate within the normal limits and commit widespread fraud. This is very hard to detect by systems that are looking for outliers or activities outside the normal band. So today, financial services firms need to augment their discrete analysis capability with connected analysis. Whether it's a fraud ring or a stolen synthetic identity, it is powerful to use a graph database like Neo4j for this purpose. So let's take a look on how modeling a fraud ring as a graph looks like. Well, organizing a fraud ring in the real world is relatively simple. A group of people share their personal information to create synthetic identities. For example, with just two individuals sharing names and social security numbers, you can create multiple different identities. And this is how these rings are born. And all these identities can then have bank accounts, social security number, credit cards, etc. And there's still nothing suspicious about the behavior for each entity until we're able to connect the dots, and then we see that these account holders actually share addresses, social security numbers, phone numbers, etc. So by looking at each user identity by itself, this doesn't become readily apparent. So imagining this data as it is expressed with nodes and relationships in a graph, this particular schema becomes something that you can detect and prevent with lightning fast queries in Neo4j. So that was just an introduction to how graphs works, and hopefully it gave you a flavor for how graphs can augment existing technologies in detecting and preventing more complicated fraud schemas. Now we're going to dig in a little bit deeper with a couple of examples of credit card fraud based on real-life scenarios. And we'll also give you a hands-on demo on how this works and looks when using Neo4j. I'm going to hand over to Nav Madhur, who is our Senior Director for Global Solutions at Neo4j, and then Ryan Boyd from our Developer Relations team is going to perform a Neo4j demo. So over to you, Nav.
Thanks, Alessandro. This is Nav Mathur, Senior Director of Global Solutions at Neo4j. Excited to be a part of this webinar. Thanks for the strong showing, folks. And let's get started on some fraud examples. The first example I'm going to talk about is related to credit card fraud. And this scenario deals with credit card testing, where a fraudster tests a stolen credit card to ensure that it has not been blocked before making any big purchases. Cards can be stolen in many different ways. Some common examples are that they can get skimmed at an ATM. That's the picture in the middle there. or you can have a card reader that has a skimmer attached, and the credit card information gets to the fraudster that way. Or there could be an illegal card reader in use. There could be cameras in the area where cards are being swiped, or there could be a data breach, which we hear frequently these days at companies that store credit card information. So these are all some very common ways that fraudsters can get a hold of thousands of credit card data, and these frauds are highly organized and have highly complex ways of testing the card and then making that big purchase. So let's get into this example here. You have a card issuer that issues credit cards to a cardholder, which in turn uses these credit cards to make transactions over a period of time. These transactions are at different merchants, and somewhere there the credit card information gets skimmed or stolen, and you now have a fraudster in possession of a stolen credit card, who then makes these fraudulent transactions, but they appear to be normal as they are pretty low dollar value. The fraudster will make increasingly higher value transactions at common stores. Like, for example, it could be doing a test at a Starbucks for a very small dollar value, which is unnoticeable to the bank and to the user because they're not paying attention to their credit card statements. And as they make these increasing dollar value transactions, they're getting more confident that the card can be used and that there are no mechanisms that are tripping off fraudulent activity on the card. And once they're reasonably sure of that, they then go to that merchant of choice, whether it's a big laptop or a jewelry purchase or whatever that big dollar purchase is. They go ahead and make that purchase at a merchant, and they disappear right after that. They throw away the card, or they basically move on to the next card or the next fraud, because at that point they're pretty sure this fraud is going to get eventually discovered, but they've already made the purchases and gone. Next, I'll be talking about a different example. This is also related to credit card fraud, but here we're looking at fraud origination and assessing loss magnitude. That's quite a mouthful, but what we're doing here is that once a transaction is reported as fraudulent, whether it's by the user of the card themselves or analytically determined by the bank, the credit card company needs to figure out where did the fraud actually originate. It may not be that particular transaction, it may be back in time, and then also determine if other people are being also affected by the same fraudster or fraud ring, and they need to also determine the magnitude of the loss in dollar value from all the fraudulent transactions across the users being affected. But right now they have only knowledge of this one person that has reported the fraud. So let's go forward. So John essentially has a bunch of transactions on his credit card, and he discovers through his statement that there is a $2,000 charge, which appears to be fraudulent, as he has not done that transaction at the computer store, and he reports that as a fraud. The bank in turn goes back, looks at the history of all his transactions, and in that cross verification they determine that this was not the point of where the fraud started or the origination of the fraud, but there have been fraudulent transactions happening, smaller dollar values that were missed. The fraud actually originated at a gas station, and so based on that information, the bank looks at other people who have been to that gas station at a in a particular time interval. Let's say in the 4 hours before and after this person was there, and they look at that window of transactions and find all the people. So they find Sheila as one person that has been to that gas station at that time, similar to John, and they look at her transaction history and they find a similar $3,000 charge at a jewelry store, which doesn't fit the pattern of Sheila's charges, and so they contact Sheila and determine that's also fraudulent. And similarly, they find other fraudulent transactions of Sheila. And going forward, they look at other people. They look at Robert, and they find that none of his transactions are fraudulent, so he's clean. It's not that every person going to the gas station at that time would have his card stolen and the fraud perpetuated. Next, they look at Karen, and again they find a similar discrepancy with her transactions. They find a $1,500 charge at a furniture store, which is fraudulent, and again, that's not the only fraud activity on her card. They trace it all back to the gas station as a point of origination, and now they and you can imagine this is not just 4 people; it's probably thousands of people who've been to the gas station that day, and a good percentage of them may be likely candidates where the fraud was perpetrated. Based on this, the bank can then figure out the total dollar amount of risk that they have in terms of these fraudulent transactions, and that's really the use case. Now, both of these use cases, as you can see, are pretty complicated in terms of traversing multiple data elements, going back in time, having location maybe as another parameter that is being looked at, and similarly, there are many other parameters that these banks and credit card companies look at to determine fraud. This is possible only in a graph database like Neo4j, because traversing these links and traversing these transactions back in time and across to other people makes it's very easy to do that in Neo4j and with our Cypher query language. So this is really a really good use case for using a graph database. So now I will turn it over to Ryan, who's going to actually demonstrate this use case in our database so that you can get a real live view of how you would write your Cypher queries to detect this fraud. Ryan, over to you.
Thanks, Nav. This is Ryan, and I'm going to give you a demo of Neo4j and show you some fraud detection queries that you might want to try out yourself later on. So this is the Neo4j browser, and the Neo4j browser is the interface that developers use to interact with Neo4j. This is meant for the developer audience and to provide that type of tooling. There are BI tools and visualization tools available from third parties that are especially designed for graphs, things like Linkurious. So you can check those out if you're looking for something for your end users. But this is the developer interface, and we can see here I've logged in, and on the left-hand side we see the different types of nodes we have in our graph. In this case, I have a card, I have merchants, I have risk scores, I have transactions, and I have zip codes. And we're going to go through some example queries here, but I just want to start a very simple thing is anyone click on the word card here or merchant, and that will actually run some queries in the database. So as you're first getting used to Neo4j, just click around and hopefully, as long as you don't have a production data set, just click around and try it out, see what each of these things do, and you can explore your database that way. So for fraud detection queries, I'm going to talk a little bit about some of the scenarios that Nav talked about and give you some demos here. So this version of the query, first of all, I want to just find our top 100 cards in our database. So we can see here the result set that I've returned is actually tabular in this case. And I'm listing out each of the card holders, their card numbers, the total number of transactions for that particular card, as well as the count of merchants that they've made those transactions at. Now, like I said, this data is tabular, which means that you can work with this data in your application the same way as you would work with any other tabular data from a different type of database, like a SQL database. Now, I'm going to show you the advantages of Neo4j and using a graph here shortly, but knowing that you can work with the data in a similar fashion in your application code is very important. Neo4j has drivers for top programming languages such as Python and JavaScript and .NET, and you can easily get up and running with those drivers. And we also have community supported drivers that are for a wide variety of languages, including PHP, Go, Haskell, and other things. And of course, the other supported driver, which I missed, is our Java driver. But all of these drivers can be used to access Neo4j and deal with the responses from Neo4j in a tabular fashion. Of course, if you're using Java, you can also use JDBC to interact with Neo4j, and that's another great way too. So you can just kind of replace your existing code that looks at your relational database and replace it with a real relational database, a graph database. So that's just a quick overview here. The tabular data format we can see, and we're doing some aggregate queries here, but let's get to some of the heart of the value of Neo4j and graph databases for looking at fraud transactions. So first of all, let's say we've identified coffee shops as an area where people frequently test, fraudsters frequently test credit cards. So if I want to look at these, I'm going to move this over here. I'm looking for merchants whose name contains Starbucks. Don't need to pick on them. It was the coffee shop which came to mind. But merchants whose name contains Starbucks, and I'm going to pass that merchant through. And then I'm going to find transactions. So a test transaction 1 is what I'm calling it as an alias, and it's a transaction labeled node, and it occurred at a particular merchant, the merchant that we referred to earlier as Starbucks. And test transaction 1 had a following transaction on the same credit card of test transaction 2, as we're calling it, and then had another transaction, a test transaction 3, as we're calling it. And these transactions were increasing amounts. So the third transaction had a larger amount than the second transaction, had a larger amount than the first transaction. And we're going to say that the first transaction was less than $10. The potential fraudster started off with a very small transaction, tested out the card, and started gaining confidence. So let's look what that returns. Well, we can see here actually a set of transactions here. This is a graph view of our data, and we can see here the test transaction 1 is this transaction, and it actually had an amount of $2. It was a very small transaction that they first tested at Starbucks. And then you can see that they went on to do test transaction 2 at $29, and then eventually had a big meal at Starbucks for $45. I'm sorry, that's not actually a big meal at Starbucks. That is just an increasing order of transaction amounts, and this could have been at some other place. So let's dive in and see actually where this transaction was at. So if I double click on this node here, we can see actually that the $45 transaction was at a furniture showroom. And so that furniture showroom, they bought something for $45, and we can see that that transaction was, all of these transactions were initiated from a particular card. So this card, a MasterCard, you can see at the bottom here, a MasterCard with a card number held by Len Yaley, a male, has made this this transaction for $45 at the Spritz Furniture showroom. And this person is the same person that made these other transactions, in this case, Adorn Me Art, and this other transaction, let's see here. Oh, this was the Starbucks transaction. So, and then there's even another transaction in between here. So these are the different places that this cardholder made transactions. But if you remember, it all started off from the very basic here of they made transactions in increasing values starting at Starbucks, which is a known potential testing point of credit card transactions. So we have our pattern of 3 in a row with increasing transaction amounts. The next transaction that comes in, we might want to potentially investigate that further. So graph databases are great that they can stop some of this fraud from occurring in real time because we're able to run these types of queries with very low latency. And the reason these queries scale so well, and Neo4j scales to web scale with people like eBay and Medium and Walmart using Neo4j for internet-facing applications. The reason it scales that well is because of a property we call index-free adjacency. What that means is that as you're traversing across these relationships, so you're traversing from one transaction to the next transaction to the merchant, and all the way back to the cardholder, each of these hops, each of these lines or arrows or relationships that you're seeing on here in a SQL database would be a join operation. And those join operations are super expensive because it's doing index lookups on each and every join. Well, with Neo4j, if we started off with a very simple pattern and started off by referencing Starbucks, we're doing an index lookup to find the Starbucks node, but then after that, as we traverse these relationships, it's literally just doing memory pointer arithmetic to find the next relationship in the graph. So this pointer arithmetic is super easy to do and super efficient to do, and that's what makes a graph database so special. So we can see here how we navigated from our card holder all the way through the different transactions that occurred, including at the Starbucks low value transaction. And we might want to look at their future transactions to make sure that they don't go buy a $2,000 TV at their local electronics store. Now let's look at some of our other saved queries, and we're going to look overall. Let's just find our risky card. So one of the properties that we stored in here was a risk score. Now risk scores oftentimes are attached to credit cards and oftentimes are actually attached to transactions as well. In this case, I'm finding risky credit cards here, and we can see actually that we have a handful of risky credit card activities, and some of these credit cards will actually have transactions in our system. So let's look there at those transactions. So these are all, I have a risk score from 1 to 5, and these are all the scores that these are all the scores that are attributed to cards where the score is 5, right? The score is the highest score that you can have in terms of risk. So we'll show you a little bit of the distribution here of our risk scores. So I'm going to match our risk scores and return r.score and the count, and we'll see here our overall distribution here. So most of our cards are actually very low risk, and we only have a handful of super risky cards. But let's look at those risky cards here. So one thing that might be important if you've identified these cards as being very risky is seeing what the overall liability is on these cards. How many dollars worth of transactions are these risky cards producing? So we're looking for cards that have attributed to them a risk score where the risk score is 5, and then that card initiates a transaction. Let's sum up those transactions and list them by the cardholder and card number. So we can see of the 5 risky cards, we have transactions in our database here for 3 of those risky cards, and it looks like one of those cards has over $14,000 in charges. So that's potential risk for chargebacks. So we're going to want to take a look more at that account and mitigate that risk. Now, so we found our risky cards, we found the liability of those risky cards. We talked about the transactions starting at the hotspots in small amounts and leading up to a potential big purchase that we want to block. Now let's look historically. If we have our jewelry purchases, let's look at the patterns of activity that led up to those jewelry purchases. So in this case here, we're going to find merchants whose name contained jewelry. Obviously, your database might have a little bit smarter thing, looking at the SIC code or something like that, or the merchant category. But for now, we're just going to look at merchants whose name contained jewelry. And then we're going to find transactions that occurred at that merchant, as well as look then at the previous transactions that occurred. So look at a potential test transaction 1, test transaction 2, test transaction 3 before making a purchase at the jewelry store. And we want to see that they made a purchase at that jewelry store for greater than $500. And if we query that, we actually get a couple matches here. So we have this transaction here, which occurred at this merchant. And this transaction, we can see here, the value is $890. I'm displaying that in the node. The previous transaction was $582. And you can see it started with some smaller transactions leading up to this big transaction at the jewelry store. And we can see that before going to the jewelry store, they actually purchased at Sur La Table. Maybe they purchased some kitchen equipment. And before, one of their less valued purchases were actually both at the Tiffany & Company. So they got some jewelry, they got some kitchen equipment, and then they went for their big jewelry purchase at what looks like probably a local jewelry store. So that is kind of seeing how you can trace up to these transactions. And we have this card here. We can then explore all of the other transactions that card made. And due to that index-free adjacency property of Neo4j and graph databases or native graph databases, it's really fast to make these queries real-time and make real-time decisions based off of them. And best yet is it's really easy to write these queries. This is the Cypher query language, and we call this ASCII art for graphs because you're essentially drawing the patterns in your graph. There's no translation that's occurring here from how the data is drawn up by a business person on the whiteboard to how the data is inserted into the database by the developer and worked within the database by the developer to how it's stored on disk to how a developer analyst queries the data. There's no translation in each of those steps. It all looks like a graph, which is a very natural view. Now, if you want to check out Neo4j and play around with it yourself with your own data, I would encourage you to look at the Neo4j sandbox. So you can just search the web for Neo4j sandbox and you'll find this. It allows you to navigate through Neo4j using a variety of different use case data sets and guides. And you can do that. You just hit get started here. And once you get started, you'll be asked to log in. In this case, I'll choose to log in with my Google account, but I can use my LinkedIn, Twitter, GitHub, or just use an email address and password. And once I'm logged in, I'm given the ability to launch a new sandbox for each of these use cases. So in this case, I'm launching a sandbox for recommendation engines so that I can learn how to build recommendation engines on graph databases. Believe it or not, recommendation engines apply to a lot of different use cases, so you want to check that out. This is about content recommendations, but I can dive right in into the Neo4j browser from there, and I get this interactive guide that guides me through the data model and different types of queries that I can do for doing different types of recommendations from data in a graph database. So we don't yet have a fraud detection use case here for you, but we'll have that in the, say, next few weeks, hopefully. And in the meantime, check out one of these other sandboxes using the Neo4j sandbox. Now let me send it back over to Nav, and Nav can go through some other content here for you. So Nav, back to you.
Ryan, thanks for that demo. Definitely makes that example very real, and hopefully you all understand how Cypher makes this so quick and easy to do a complex query like this to determine fraud and prevent it. So let's move into the architecture and talk about how Neo fits in an overall architecture for credit card fraud. So let's start with, to keep up with all these complex schemes fraudsters are employing, a lot of this complex data that's coming from transactions and other such data is being stored today, or has been traditionally stored in relational databases. And you might have multiple such databases with different types of data. And in the past, this was good for discrete analysis, as Alessandro talked about, where you're doing sort of point analysis on the data locally within one data store and not able to really traverse relationships. So you don't get a holistic view of those data relationships, and the query speeds are pretty slow, especially if you try to join across multiple tables or across multiple data stores. And so the data science team was not very useful in uncovering complex fraud schemes. Fast forward to today, most large organizations, banks, financial services companies, credit card companies are using technologies like a data lake to basically bring all of this data in. It could be transaction data, merchant data, data related to credit scores, and other third-party data in a central place like a data lake, where they can then start to make sense of the data, understand the patterns, run algorithms like centrality and shortest path type algorithms to figure out patterns. But they still don't have a holistic view of the data. They cannot visualize the data. They're not able to make this data operational. So once they find the pattern, they can't really operationalize that right away. This is more sort of done in a batch mode. And it takes weeks and months to do this data processing and crunching to find the patterns and then find all the patterns across the entire data set. So they are more useful, but because of the timeliness of this data and the need to prevent fraud, this is not ideal. In order to make it more ideal, if you introduce Neo4j, a graph database, into this architecture, by loading the relevant data from the data lake into Neo4j. So what I mean by relevant data is, let's say a credit card company has, 1 billion transactions in the data lake, and then they have a lot of data related to those transactions, like merchant data, credit score data, and other third-party data. But for the particular pattern, like the credit card testing that we talked about, they may need only a few of those attributes for that pattern. So not all of the data and all the attributes related to the data have to be loaded into Neo4j. So that only the relevant data gets loaded into Neo4j, and then that pattern can be easily visualized in Neo4j, and these would be some instance of the pattern that were found earlier within the data lake. Once this pattern has been visualized, you can actually remove some of the false positives, and we could also find other elements or transactions that were really part of the pattern but were not discovered. But when you look at it visually, it's pretty clear. So those type of fine-tuning of the pattern can be done with Neo4j. In addition to that, you can now run that Cypher query across the entire data set, which all the 1 billion transactions very quickly, very fast. So we're talking now minutes to hours instead of weeks and months. And once you do that, you have all the patterns and instances of the pattern discovered. You can then now do something very interesting. You can start putting together this sense and respond architecture, where you start bringing in some of the key aspects of a transaction. Again, not the entire transaction, but some of the key attributes of the transaction that are important for this use case directly from the source into Neo4j. You can pattern match against the patterns already discovered and see if they're similar. If they're similar, then you can actually kick back an alert, a notification. You can even stop the transaction. But this is where Neo4j can really be instrumental in preventing fraud in real time by stopping that big $4,000 transaction, as we saw earlier, in real time, based on sensing the pattern and then blocking that transaction. Or in other cases, you might not want to block it, but you might want to throw up an alert or a notification or kick off a process. All of that can be done by employing Neo4j in this architecture. The other point is that if you're talking about some other use cases where you don't have so much data to deal with that you don't need a data lake, you can bypass the data lake. So you can actually load data directly from the different data sources into Neo4j and connect them together and build the relationships in Neo4j and discover the patterns in Neo4j as well. It's just when you're talking about banking and fraud and the amount of transactions and the amount of data that this data lake-based architecture is more prevalent. So this is how Neo4j fits, and I'll be very interested to hear, how you guys are using Neo4j in your situation. I think that's it from an architecture perspective. I'll hand it back to Alessandro to recap, and thank you for listening.
Okay, let's do a quick summarization of this presentation. Today we talked about the complexity of today's fraudsters. We went over some examples of fraud, like fraud rings, credit card testing, fraud origination, and how you can apply graph technology to effectively help prevent these types of fraudulent activity. We'll also show you an example of how Neo4j fits in an existing fraud detection architecture. And the reason why institutions choose Neo4j is because it provides them with the capability to detect and prevent fraud in real time. From a customer experience perspective, it allows companies to perform faster credit risk analysis and transaction, and it also reduces chargebacks. And perhaps most importantly, it provides them with the ability to quickly adapt to new methods of fraud. So Neo4j is widely adopted for this particular use case. But by the nature of the fraud detection business, we can't reference clients as we usually are able to do. But Neo4j is used by top global financial institutions, government functions all over the world, typically for money laundering, tax evasion, and those kind of fraudulent activities, as well as many retailers. And that was all we had for this presentation. But before we end up, we also want to give you a shout out for some valuable resources for those of you who want to explore more on your own. If you're a developer or curious to play around with Neo4j, please visit our sandbox at neo4jsandbox.com. If you're interested in case studies and solutions regarding fraud detection, there's a lot of interesting use cases and case studies at our solutions webpage for fraud detection at neo4j.com. use cases/fraud detection. And if you want to learn more about the product in Neo4j, please visit our product page at neo4j.com/product. That was all we had for you in this presentation, and thank you very much for listening.